Have you ever wondered, what the heck is quantum computing? I am Felix.
And I am Ruby.
And today we are about to dejargonize quantum computing.
It's a term we hear a lot, but it can sound pretty complex. What exactly is it?
At its core, quantum computing is a new form of computation. It operates using the rules of quantum mechanics, the physics that governs how particles behave at the atomic and subatomic levels.
So it's processing information in a fundamentally different way than the computers we use daily?
Exactly. A classical computer uses bits, which are always in a state of either 0 or 1. There's no in between.
Right, the basic building blocks of all digital information.
Quantum computing, on the other hand, uses qubits. A qubit is unique because it can exist as a combination of both 0 and 1 at the same time.
A combination of both? How does that work?
In general, this state is called superposition. It allows quantum computers to explore many possibilities in parallel, which is something a classical computer simply can't do.
That's a bit hard to visualize. Is there an analogy that can help explain it?
There is a great one. Think about solving a very large maze. A classical computer would approach it by walking down one path, and if it hits a dead end, it backtracks and tries another path. It's a methodical, one path at a time process.
Okay, that makes sense. It would eventually find the exit, but it could take a very long time.
Now, imagine how a quantum computer would solve it. It's less like walking and more like pouring water into the maze's entrance.
So the water would spread out and explore all the corridors at the same time?
Precisely. When it's set up correctly, the water flowing into dead ends cancels itself out, while the water that finds the path to the exit reinforces itself. You're not just trying every route faster, you're using the structure of the problem so the right answer emerges as the strongest signal.
That's a powerful concept. So does this mean we should expect quantum computers to replace our laptops and smartphones in the near future, just as a much, much faster version?
That's actually one of the biggest misconceptions about them. The honest picture is that quantum computers aren't just faster versions of regular computers that will take over all computing tasks.
So they won't be used for everyday things?
Exactly. They are highly specialized machines. They're designed to outperform classical computers, but only on very specific types of problems.
What kind of problems are we talking about?
Think of things like simulating molecules, factoring large numbers, and certain complex optimization tasks. These are areas where classical computers struggle.
So for sending an email or working on a spreadsheet, my current computer is still the best tool for the job?
Absolutely. For those everyday tasks, a classical computer is faster, cheaper, and far more reliable.
You mentioned reliability. Are today's quantum machines not very reliable?
That's another key point. The quantum machines we have today are quite error-prone. They also require incredibly specific and highly controlled environments to function at all.
What kind of environments are needed?
We're talking about extreme conditions, such as needing to be kept at near absolute zero temperatures. So you can see they're not exactly designed for your desk at home.
That's fascinating. So putting aside the extreme operating conditions, what is actually happening at that quantum level? How do they perform these specialized calculations?
It really comes down to three core principles of quantum mechanics: superposition, entanglement, and interference.
Let's break those down. We touched on superposition earlier, which is the ability of a qubit to be a mix of both 0 and 1 at the same time.
That's right. A qubit, which is often a physical system like a supercooled circuit or a trapped ion, can hold this blend of states simultaneously. It's important to understand this is a real physical state, not just a state of indecision.
Okay, so that's the first pillar. What's the second one? Entanglement?
Entanglement is a truly remarkable phenomenon. It's when two or more qubits become linked in such a way that the state of one is directly tied to the state of another, no matter how far apart they are.
Instantly linked, even across distances? That sounds almost like science fiction.
It does, but it's a real property. This correlation allows quantum computers to represent relationships between variables in a way that's far more compact and powerful than what classical bits could ever achieve.
So you have superposition allowing for multiple states and entanglement linking those states. What's the third pillar? Interference.
In general, interference is how you get to the right answer. Quantum algorithms are designed so that the calculations leading to wrong answers cancel each other out, much like sound waves can silence each other.
And the correct answers?
In general, the correct answers add up and reinforce each other, again, similar to how sound waves can amplify one another. This process is crucial because it makes sure the solution you're looking for becomes the strongest signal.
So when all these principles work together, there's a final step to get the answer, right?
That's correct. When you measure a qubit, its superposition collapses and it settles into a single value, either a 0 or a 1. The whole goal of a quantum algorithm is to make sure that the answer you're looking for is the one that is most likely to appear.
It's an incredible process. So if we manage to scale this technology successfully, why is it so important? What are the real-world problems it could solve?
In general, the potential is truly transformative, especially in areas like drug discovery, material science, and cryptography.
How could it change drug discovery, for example?
It would allow us to simulate molecules with a level of accuracy that is simply impossible for classical computers. This could dramatically accelerate the process of designing new medicines and creating revolutionary materials with specific properties.
That would be a massive leap forward. You also mentioned cryptography. What's the impact there?
This is a major one. Quantum computers could potentially break some of the most common encryption methods that are currently used to protect our data online.
So the very foundation of our current online security could be at risk?
That's the challenge it presents. It's a double-edged sword, and it's why there's a global race to develop new quantum-resistant encryption methods.
With such enormous potential, both for good and for disruption, how close are we to having a practical, fault-tolerant quantum computer?
That is the subject of intense research and debate. The exact timeline is contested and changes rapidly as new discoveries are made. The challenges in building such a machine are immense, so while the potential is there, it's still on the horizon.
That brings us to the end of the episode. If you think we helped you de-jargonize the term, make sure to subscribe and follow us wherever you get your podcasts.
See you on the next episode.